In Chapter 7, we will be covering intermolecular forces. To get a better feeling of intermolecular forces, make sure you review the material that covers polar versus nonpolar chemicals. When we talk about matter, matter takes on 3 different phases. It actually takes 4. The 4th phase is plasma. Plasma is a state in which you have a gas chemical with all the electrons stripped. But that occurs at the surface of the sun, where there's a lot of energy. Here on Earth, we have the 3 states that we know as a solid, liquid, and gas. Here, what you see is, take for example ice. Ice is the solid form of water. If you heat ice, then it liquefies and forms liquid water. If you heat liquid water, then it vaporizes and forms gaseous steam. If you take that steam and cool it down, you condense liquid water, and if you cool that down further, you get ice back. And so here is an example of the 3 phases of matter: solid, liquid, and gas, and the process by which they convert from one phase to the other. When you take a solid and you heat it up, it melts. When you take a liquid and you heat it up, it vaporizes. You can actually take that gas and, under the right conditions, say at high pressure, you can deposit it. This is called a deposition, and it's also called crystallization. And likewise, you can take a solid and, under the right condition, convert it to a gas directly. That's called sublimation. If you take the gas and cool it down, you get condensation, and you get it back to a liquid. And if you take that liquid and cool it down further, then you have the freezing process. So make sure you understand the phases of matter and the process by which they change. This is what we call a heating-cooling curve. And in the heating-cooling curve, you start here with temperature on the y-axis and heat added on the x-axis. If, for example, you have water and you have it at minus 40 degrees, then that water will be solid ice, and that's what you see right here. Now, if you take that solid ice and you heat it up and add energy, that would be along this line, the temperature of that solid ice will rise until you get to 0 degrees Celsius or 32 degrees Fahrenheit. At 0 degrees Celsius, the solid matter, the crystalline solid of water, starts breaking up. And this is because intermolecular forces, which we will be studying more in this particular chapter, starts breaking down. What happens is that the crystalline solid starts to separate, and they start tumbling upon each other. Then you get to the liquid state. This happens at 0 degrees, and if you have 1 gram of ice, it takes 80 calories per gram to take solid ice and convert it to liquid water completely at 0 degrees. That phase change occurs at a constant temperature. When the last crystal of solid finally melts, then and only then does the temperature rise. And then you get liquid water heating up, and for every 1 calorie that you put in of energy, the temperature goes up 1 degree. And this is what we call the specific heat. 1 calorie per gram per degree. And for water, that's the number that you would use. If you want to use joules, 1 calorie, remember, is 4.184 joules. So what happens is that if you put in 50 calories, that 1 gram of water will go up in temperature to 50 degrees. You put another 1 calorie, it'll go up 1 degree. If you go from 50 degrees to 100 degrees by adding an additional 50 calories, then reach 100 degrees. And at the molecular level, what's happening is that the water molecule starts to move faster. At 100 degrees, they have enough energy to escape the interface and they go off into the gas phase. But that happens at a constant temperature. It takes 540 calories to take that 1 gram of liquid water and convert it completely to gaseous steam. Only when the last drop of water is converted to steam will the temperature of that steam start to rise. And so what we have here is the heating cooling curve, and it tells you how much energy, whether you're talking about calories, joules, kilojoules, how many calories you need in order to change the temperature of 1 gram of water. Here again is another illustration of the different phase of matter. Again, I want to illustrate what happens at the atomic level. When you have solid ice, the water molecules are ordered and in a fixed array. As you heat it up, then they start moving faster until they start melting. And liquid water, you have the water molecules tumbling upon each other. If you heat it up further, then they separate and form a gaseous steam. And so that's what we have here.
When heat is applied to a solid, its temperature and vapor pressure increase with increasing temperature because the molecules of the solid have increasing kinetic energy. At the melting temperature, heat is absorbed as the solid is converted to liquid at a constant temperature. When melting is complete, the temperature of the liquid and its vapor pressure increase. At the boiling point, temperature remains constant as heat is absorbed to convert the liquid to the gas phase. When all the molecules are in the gas phase, the temperature again increases as the gas phase molecules acquire additional kinetic energy. On this graph of time versus temperature, the first segment represents heating of the solid. At point A, the solid melts. The temperature remains constant while melting occurs. At B, all the solid has melted, and the temperature again increases as the liquid is heated. At C, the liquid boils. Again, temperature remains constant with time until all the liquid has been converted to gas at point D. Then temperature again increases as the gas is heated.
So that movie basically summarized the previous slide that I talked about in the heating cooling curve. Now, what is intermolecular forces? Well, intermolecular forces is what keeps matter together. But make sure you understand the difference between intermolecular forces and intramolecular forces. Intra means within a chemical or within a body. Inter means between chemicals or between bodies. So if you have intramolecular forces, these forces is what keeps molecules together. Examples are like bonds, either covalent bonds or ionic bonds. Intermolecular forces, however, are the attractive forces from one chemical to the others, and this is responsible for the phases of matter. So if you have one water molecule and it's being attracted to another water molecule, or in this illustration, one ethanol molecule being attracted to another ethanol molecule, then that's called intermolecular force. And there are several types of intermolecular force that we will be looking at in this chapter. There are two basic types of intramolecular force. I told you these were bonds. The first one is ion-ion or electrostatic. That is the force responsible for ionic bonds when sodium is attracted to chloride in NaCl. Covalent bonds are the mutual sharing of electrons, however. When a bond forms between a hydrogen atom and another hydrogen atom, then It's tied together because the electrons are shared. These are intramolecular forces. In intermolecular forces, forces between one chemical and another, there are 5 basic types. We will concentrate on 3 types of intermolecular forces in this particular chapter. One is ion dipole. When an ion is attracted to a polar molecule, this is ion dipole. For example, when water dissolves sodium chloride, for example, the water orientates itself and pulls the sodium or the chloride out from the crystalline lattice of sodium chloride. There's also a dipole-dipole interaction, and this occurs when you have one polar molecule attracted to another polar molecule. And in chapter 6, what you saw was that water molecules like to attract each other because they have a positive and negative end in one side of the molecule, and so it's like a magnet. The positive is attracted to the negative, and this is called dipole-dipole interaction. It occurs only for polar chemicals. Then there's dipole-induced dipole. That's when a polar chemical causes a nonpolar chemical to be attracted to it. So this is a type of intermolecular forces that we will not study much, but it's also the mechanism by which oxygen is able to dissolve in water. Imagine if oxygen wasn't able to dissolve in water, then the water, the ocean, would lack oxygen molecules and all the marine life would die. So this is a very important intermolecular force. The fourth intermolecular force is induced dipole-induced dipole. This occurs for all chemicals that have electrons. So what happens is that the electrons are going to orientate themselves within a chemical so that one side is positive, the other side is negative. And it creates a positive attraction to another nonpolar chemical. And so we will look at this more closely later on, but it's called induced dipole, or better known as London dispersion force. It's most significant for nonpolar chemicals because for nonpolar chemicals, this is the only type of intermolecular forces it tends to exhibit. There is one more, and we will talk about that last intermolecular force in a later slide. So, how are ion intramolecular force created? Well, if you go back to earlier chapter, you'll know that some chemicals have extra electrons, some chemicals have deficient electrons. And so what happens is that they want to form an octet so that they have a total of 8 electrons in its outermost shell. And so an example would be sodium fluoride or sodium chloride. Sodium has 1 valence electron in its outermost shell. Fluorine has 7. By donating that 1 electron to fluorine, both atoms now has an octet and they're totally happy. The sodium positive and the fluorine negative are going to be attracted by electrostatic interaction. That's an ionic bond. That's ion-ion intramolecular force. That force is generally about 910 kilojoules per mole. When an atom, a non-metal atom, wants to accept electron, for example, this fluorine atom should have 9 valence electron. By sharing that electron, that odd electron, it'll have an octet. The bond created by this covalent bond is about 155 kilojoules per mole. Now, let's review polar versus nonpolar chemicals. Remember that atoms want to have electrons. They tend to draw electrons because of the protons. So what happens is that when 2 atoms are sharing electrons, If one atom is stronger than the other, then the electron is going to reside more strongly to that atom that has a stronger tendency to pull those electrons. You can liken this analogy to a tug of war. If you've got two teams tugging in opposite direction with equal strength, then there's no winner in this tug of war. On the other hand, if you have two teams and one team is stronger than the other, then there will be a winner in this tug of war game. And so if two atoms are tugging on electrons and one atom is stronger or has a stronger attraction for electron than the other, then the electron density is going to be skewed, and so you have a distortion of the electron cloud, and so you have a polar situation, a polar molecule. Now, this situation can be more complicated because you have like 3 or 4 teams. Suppose we have 3 teams and they all have equal leverage among each other and they all have equal strength. Well, in this situation, there is no winner in this tug of war game. And so this would be a non-polar situation. Suppose, however, that in this 3-team tug of war, one team is stronger. Let's say we have an atom that tugs more strongly towards those electrons than the others. Then there is a winner in this tug of war game and we have a polar situation. Now, take this scenario right here, the third case, where one team doesn't have the leverage in order to draw those electrons because the geometry is not quite symmetric. Well, what happens is that these two will combine forces and there's going to be a drawn of that centerpiece towards the middle between these two, and therefore, since there will be winners, in this case 2 winners in this tug of war game, you have a polar situation. So in order to determine whether a chemical is polar or non-polar, you have to first figure out whether or not you've got symmetry in that chemical, all atoms at the terminal being equal, and whether or not the geometry is symmetric. Let's look at the relative strength of these intermolecular forces and just take a look at which one is the strongest and which one is the weakest. And it's not really black and white. Some of these intermolecular forces overlap each other. Now, these two are just intramolecular force. Okay? Ion-ion covalent bonds. Ion-ion, the energy generally to break a bond is 400 to 4,000 kilojoules per mole. That's the range. For covalent bond, it's weaker, but it's still pretty high. It's about 150 to 1100 kilojoules per mole. Now let's take a look at intermolecular force. The ones that you need to remember in this class are going to be dipole-dipole, London dispersion force, and something called hydrogen bonding. The ones that you're going to have to remember in this class are dipole-dipole, London dispersion force, and then the fifth, which we call hydrogen bonding. Ion dipole, 40 to 600 kilojoules per mole, depending on the species. Dipole-dipole goes between 5 and 25. So there's some overlap depending on the chemical. Ion-induced dipole, it's about 2 to 10 kilojoules. London dispersion force, it's about 0.05 at the lowest, but up to 40 at the highest. And you notice that that high end could easily overcome the low end of dipole-dipole. So some London dispersion force can actually be stronger than dipole-dipole. And then something called hydrogen bonding. Well, if we're studying dipole-dipole and London dispersion force, well, hydrogen bonding can certainly be very, very strong relative to those two types of intermolecular force. Before we move on and look more closely at intermolecular force, we have to figure out how these intermolecular force manifests itself on the properties of matter. And the properties of matter that we will be discussing is like the boiling point or the melting point. Heats of vaporization, that's how much energy you need to cause matter to vaporize. Heat of fusion, that's how much energy you need to melt a solid. Specific heat, amount of energy you need to raise the temperature 1 degree. Heat capacity, how much energy you need to raise 1 gram of substance 1 degree in temperature. Specific heat and heat capacity, we will talk more about that shortly. Okay, surface tension, that's basically the energy at the surface of a liquid interface. Capillary action, capillary action is how chemical is attracted to each other versus how chemicals are attracted to another surface. Viscosity, that's just the resistance for flow. And vapor pressure, that's basically how well a chemical will vaporize. Now if we take a look at boiling point. Boiling point, the process of boiling is when the molecule starts to move faster from the liquid state so that they can escape to the gas phase. So imagine molecules that are attracted to each other very efficiently. It'll take a higher temperature to boil them because you have to break that hold between one chemical to another. So the stronger the forces between the chemical, the higher the boiling point. The melting point, if the chemical and the solid phase have a great attraction for each other, then the melting point will be higher if you want to separate them so that they're tumbling among each other. So if you have strong intermolecular force, if you have strong force between the chemical, then the melting point will be higher. Heats of vaporization, that's how much energy you need to put in to get a liquid into the gas. Again, if the chemical is strongly attracted to each other, then it'll take more energy to separate them into its gas phase. Heats of fusion, that's the amount of energy that you need to take a solid into a liquid state. And again, the more efficient those chemicals are in grabbing each other, the more energy you need in order to separate them and cause them to melt. Specific heat, that's the amount of energy you need to take a chemical, generally a liquid, and raise it 1 degree. Heat capacity, heat capacity is taking a substance that is in the same phase and just changing its temperature. If you take, for example, a carbon rod versus an aluminum rod. Carbon is a good, it has a high heat capacity. Aluminum, on the other hand, has a low heat capacity. In other words, the aluminum, if you heat one end, the temperature easily changes. Carbon and water, if you change the temperature or you add energy, the temperature doesn't change that significantly. And so what we say is that water or carbon, in our example, has a high heat capacity. Surface tension. If the chemicals are attracted to each other at the surface of an interface, then that tension will be stronger. Capillary actions, similar to surface tension. If they are attracted to each other, they will try and minimize the surface area, and then if it's attracted to, say, a wall, a glass tube, it'll rise up. Viscosity. Viscosity, when you have strong intermolecular forces between chemicals, then they will tend not to break up. They'll tend to flow very slowly when you try and roll it down an inclined plane. So all these properties that we've talked about, the stronger the intermolecular force, the higher the properties. All except that last one, the vapor pressure. Vapor pressure is the pressure that the gas exhibit once you heat a substance. And so imagine if you have a glass of water and a glass of alcohol. Water has strong intermolecular force, and so if you heat it up, not much of it will go into the vapor phase. And so what happens is that it has low vapor pressure. If you have alcohol, however, like ethanol, it easily evaporates. That's because its intermolecular forces are generally very weak. And so if you heat it up, it goes off into the gas phase, and it easily creates gas, which if you enclose it will create pressure. So for vapor pressure, the weaker the intermolecular force, the higher the vapor pressure. Think about these properties as we talk about intermolecular force, because this is how we gauge the strength of the intermolecular force, by measuring properties, by looking at the properties that are easily measured. Let's take a look at ion-dipole interaction. The most important thing about this type of interaction is that the larger the charge and the smaller the size of the atom, the more significant that intermolecular force. Lithium is a smaller atom than cesium. It has a 90 picometers radius versus cesium, which is 181. Look at the enthalpy of hydration, that is the energy needed to hydrate these chemicals. Lithium is 515, cesium is 263. So again, these are the type of intermolecular forces that is between an ion and a polar molecule. Don't worry too much about this type of force unless you're taking advanced chemistry. Let's take a look at dipole-dipole interaction. And remember that dipole-dipole interaction occurs for polar chemicals. Now, the chemicals here on the left are all nonpolar. These are its boiling point. The molar mass of nitrogen is 28. The molar mass of silicon tetrahydride is 32. Uranium tetrahydride is 77, bromine is 160. These molecules over here are all polar. The molecular weight of carbon monoxide is 28, pH 3 is 34, ASH3 is 78, and ICl is 162. The message here is that these chemicals are all very comparable in size, except that these chemicals to the left are nonpolar. This chemical to the right are polar. These are the boiling point. You can see that the smaller the chemical, the lower the boiling point, which tells you essentially that it has a lower intermolecular force. But take a look at these chemicals versus these chemicals. What happens is that the boiling point for nitrogen is minus 196. The boiling point for carbon monoxide is minus 192. A lot higher than nitrogen. And the only difference here, because they have the same molar mass, is that this chemical, carbon monoxide, is polar. Let's look at SiH4 versus pH3. This has a boiling point of minus 112. pH3 has a higher boiling point at minus 88. Again, because pH3 is polar. Likewise for these other two. The polar chemicals have stronger intermolecular forces than these nonpolar chemicals, thus giving it a higher boiling point. Now let's take a look at induced dipole, and let's figure out the mechanism by which this works. Basically, you have a chemical with protons and electrons, and it's sitting in an array or in an aggregate of other chemicals. Now, what will happen is that every once in a while these electrons are moving about, but what happens is that the electrons might cluster to one side of the chemical versus the other, and so this side is what we call partially negative because there's a more abundance of electrons in this side. It happens only for an instant, but it's enough to cause this wave. If the electrons bunch up on this side so that this side's partially negative, then the opposite must be partially positive. Well, a neighbor will recognize that partially positive side and the electrons will bunch there. And so it creates an induced dipole in its neighbor, and then this series continues down the chain. So this is what we call London dispersion force. It's most significant the more electrons you have. It's true for all chemicals because all chemicals have electrons, but the more electrons you have, the stronger the London dispersion force. This is what we call the polarizability factor. It's the ease of which an electron cloud can be distorted. Larger the atomic size, the greater the number of electrons, the greater the polarizability. So let's take a look at the data here. We have fluorine, chlorine, bromine, and iodine. Fluorine is a much smaller molecule than iodine. Look at its boiling point in Kelvin. 85 versus 238 versus 332 versus 457. In fact, at room temperature, iodine is a solid, indicating that it has much more stronger intermolecular force because of London dispersion force than fluorine. Let's take a look at atoms, noble gases. All these have electrons. Helium is a smaller atom than neon, which is smaller than argon, which is smaller than krypton, which is smaller than xenon. Because xenon is more polarizable, what we have is that its boiling point reflects that. Its boiling point is 166.1 Kelvin versus helium, which is only 4.6 Kelvin. Practically 5 degrees above absolute zero. So, what we've learned is that the bigger the chemical, the stronger the intermolecular force. Remember that all chemicals, because all chemicals have electrons, have London dispersion force. For polar chemicals, on top of London dispersion force, they also have dipole-dipole interaction. Non-polar chemicals, all they have is London dispersion force. So if we look at this graph right here, and we look at a series of carbon, silicon, germanium, and tin, they're all in the same column. They're all in the same family. CH4, SiH4, GeH4, SnH4. It makes sense that for the boiling point, the temperature goes up because tin tetrahydride is a bigger chemical, therefore stronger London dispersion force than germanium tetrahydride, which has a higher boiling point than silicon tetrahydride, which has a higher boiling point than methane, CH4, carbon tetrahydride. Likewise, if we go to the next element down the line, sulfur, selenium, tellurium. Tellurium, H2Te, is going to have a higher boiling point, which is higher than tin hydride because tellurium is a bigger chemical than tin. H2Te, tellurium hydride, is going to have a higher boiling point than selenium hydride, which has a higher boiling point than sulfur dihydride. You would expect, based on this trend, that oxygen dihydride or dihydrogen monoxide would have a boiling point of about -100. Instead, what you see is that, and this is, we continue down the chain, the series here. What you see is that water, H2O, this trend right here in blue, goes up, not at -100, but at +100. If we look at the halogen series, what you see is that the last chemical, HF, goes up. If we look at the nitrogen family, we see that the last chemical likewise goes up. And so there's something happening for these very light chemicals. What is it that is causing them to have stronger intermolecular force? And that force, that extra glue, is called hydrogen bonding. The hydrogen bonding adds to the London dispersion force that the chemical has, and it's like an added extra glue. What exactly is hydrogen bonding? Well, hydrogen bond occurs because the oxygen nitrogen, and fluorine are all very small chemicals. And because they're all very small, much smaller atoms, they have a stronger affinity for the electrons that it's supposed to be sharing, that it's pairing up with its partner. It's a special glue that is above and beyond the dipole-dipole and London dispersion force. And it only occurs when hydrogen is attached to nitrogen, when hydrogen is attached to oxygen, when hydrogen is attached to fluorine. Why? Because these atoms are highly electronegative. Likewise with chlorine. They're highly electronegative because, one, they have a lot of protons relative to their electrons in the valence shell, and they tend to be small. And they add an extra 10 to 40 kilojoules per mole of energy in terms of intermolecular force. In fact, hydrogen bonding is so important that it's necessary for life. Biochemical structure is based on hydrogen bonding. The unique properties of water is based on hydrogen bonding. Take, for example, protein structure. We have a primary, secondary, tertiary, quaternary structure. The secondary structure, the way it folds, is based on hydrogen bonding. The way the tertiary structure as well, the way it bends with each other, is based on hydrogen bonding. If it wasn't for hydrogen bonding, the protein structure would not be correct and these proteins would not function correctly. DNA, RNA, it's all based on base pair. Base pair is attracted to each other by hydrogen bonding. The way DNA unwinds and makes duplicates of itself is based on this hydrogen bonding. Hydrogen bonding is just strong enough to keep the molecule intact, but weak enough so that it can come apart and come together again if necessary. This right here is a summary of how intermolecular forces presents itself into the properties of chemical. So let's take a look at the following example and determine whether or not these chemicals have the presence of hydrogen bonding. Remember to look for hydrogen bonded to an electronegative element. First one is ethane. There's hydrogen here, but there is no electronegative element. This has no hydrogen bonding. Here you've got OH. Wherever you see OH, it's always the presence of hydrogen bonding. Likewise here, OH, hydrogen bonding, hydrogen bonding. Here you have nitrogen, oxygen, and hydrogen. The hydrogens themselves are not bonded to oxygen, but they are bonded to nitrogen. So you have the motif that is necessary for hydrogen bonding. Here what we have is you've got oxygen and hydrogen, but the hydrogen's not bonded to oxygen, so you don't have hydrogen bonding here. Here you have fluorine, and here you have hydrogen, but they're not bonded to each other, so there is no hydrogen bonding here. And here you have oxygen, but not bonded to any hydrogen, so there is no hydrogen bonding here. So let's take a look at the answers. No for ethane, yes for ethanol or methanol, yes for this chemical because of the NH group right here, no for this next one, yes for E, that's acetic acid by the way. This right here is ethanol, this right here is acetone, no hydrogen bonding in acetone, and this right here is aldehyde, no hydrogen bonding there. So let's do another example. Identify the type of intermolecular forces that each of these chemicals possess. And the key to answering these questions is first determine whether it's polar or nonpolar. A chemical like C2H6, that's nonpolar. It's totally symmetric. This chemical right here, it's got oxygen and hydrogen. This is polar. This chemical right here, it's not quite methane. It's got fluorine, so it's not totally symmetric. This is polar. This chemical right here, because it's symmetric, even though you have an oxygen in the center, this is polar. NH3 is polar. This chemical right here, because there's non-symmetry in these chemicals, these are two is polar. When you're determining the type of intermolecular force a chemical has, make sure you check off London dispersion force for all chemicals. All chemicals have London dispersion force, so you want to check this off. Dipole only occurs for polar chemicals. Which chemicals did we say was polar? This chemical, this chemical, this chemical, and this chemical. 4 of the 6. And then hydrogen bonding, look for hydrogen bonded to an electronegative element. This guy, 2 of these chemicals contain hydrogen bonding. So let's take a look at our answer. London dispersion force. This one has London dispersion force, dipole, hydrogen bonding, polar. This guy is also polar. It's got London dispersion force, dipole. No hydrogen bonding because the hydrogen is not bonded to fluorine. This next chemical, this is polar, it's London dispersion force. It looks like it's non-polar, but if you do the molecular geometry for this chemical, what you will find is that oxygen has 2 lone pairs, which causes it to bend. This is a tetrahedral oxygen. It's a bent configuration, so it is slightly polar. So it's going to have London dispersion force and dipole. NH3 is polar, London dispersion force, hydrogen bonding. This right here, F3CNF3, this is a polar chemical. It doesn't have hydrogen bonding. It definitely has London dispersion force. Let's take a look at this next example. If you take a look at this example, identify the dominant intermolecular force for each substance, select the dominant intermolecular force, and select the substance with the higher boiling point. Well, this is an ionic substance. This is a covalent substance. How do you know? This has a metal, this has no metal. Ionic, covalent. This chemical right here has ion dipole. I don't expect you to know that, but I do expect you to know that it has London dispersion force. This chemical has dipole because it's polar. It's like NH3, and it's also got London dispersion force. The higher boiling point is always going to be the ionic chemical. This chemical right here has hydrogen bonding. This is polar. This right here has no hydrogen bonding. It is polar. So this has dipole and London dispersion force. This has London dispersion force, dipole, and hydrogen bonding. I would say that this chemical right here has the higher boiling point. This is methanol, this is ethanol. They both have hydrogen bonding, they're both polar. They both have London dispersion force, but this is a bigger chemical, so its London dispersion force is going to be significantly stronger, and so this would have the higher boiling point. Hexane and cyclohexane. Both of these are hydrocarbons. They're both non-polar. The key here is that cyclohexane is a cyclic chemical. Hexane is a straight chain. Hexane will have more surface area than cyclohexane. Hexane, because it has more surface area, its electrons are more exposed. Both will have London dispersion force only. Hexane will have the higher boiling point because it has more surface area. More of the electrons is exposed. This is a summary of the type of intermolecular forces that we talked about. Now recall that we talked about properties of matter and how those properties, recall that we talked about properties of matter and how intermolecular force manifests itself in these different properties of matter. Recall that we have three states of matter that we are used to, the solid, liquid, and gas, and that these phases of matter depends on intermolecular forces. When the intermolecular forces are strong, it tends to be a solid. As you weaken that intermolecular force because you apply heat, then it converts to a liquid. If you weaken that intermolecular force even further, then it goes into a gas. Remember that intramolecular force are bonds, either ionic or covalent. Intermolecular force that we are going to concentrate on are dipole-dipole, which occurs for polar chemicals, London dispersion force, which occurs for all chemicals but is most significant for non-polar chemicals, and hydrogen bonding, in which in that chemical it has hydrogen bonded to an electronegative element. So what is the unique property of water that arises because of hydrogen bonding? Well, density-wise, which is the mass of a substance for the volume it occupies, we're going to look at these properties: surface tension, capillary action, specific heat, heats of vaporization, heats of fusion, heats of vaporization, viscosity, boiling point, melting point, and vapor pressure. We're going to take a look at all these properties and see how the unique hydrogen bonding of water tends to change the properties of water because of the hydrogen bonding properties. If we take a look at water, water has a very low density in its solid state. Why? Because the properties, density. For water, it has a low density in its solid state. In fact, in its solid state ice, it tends to float versus sink. Surface tension for water has a very high surface tension. In fact, you can float a penny on water if you put it just right. Capillary action, well, the capillary action of water is one of the highest. Specific heat for water, it's among the highest among liquids and solid. Viscosity, it's pretty high. Other chemicals also have high viscosity, but for water it's pretty high for a very, very small chemical. Boiling point and melting point, exceptionally high, as well as its heats of vaporization and heats of fusion, and the vapor pressure tends to be low. For water, the specific heat is 4.184. The heat of fusion is 333 joules per gram. The heat of vaporization is 2,250 joules per gram. Surface tension is pretty high. It's a great conductor of heat. Viscosity, less than most liquid, but still pretty high. And dielectric, which is how well it conducts electricity. So water is also a universal solvent, and the reason why it's a universal solvent is because it can dissolve both ionic substance and covalent substance, and it dissolves covalent substance because the covalent substance that it tends to dissolve is polar. Take, for example, this illustration right here. If you have water and carbon tetrachloride and iodine, that's what you see right here. Water is a polar chemical and carbon tetrachloride is a non-polar chemical, and so what you see is a separation. If you take iodine and you put it into this mixture, Iodine is nonpolar, so it'll go into the carbon tetrachloride. A small amount of iodine is going to go into water, but not a lot. And so what happens is, in the second picture, the mixture is then stirred, and the nonpolar iodine is more soluble in carbon tetrachloride. That's what you see right here. And it doesn't go into water. Remember that carbon tetrachloride is much more dense. That's why you see it in the lower layer compared to water. Reason why the water is discolored is because a small amount of iodine is going to be dissolved in water, but when you shake it, it all goes to the nonpolar chemical. The density of water is one of the highest. This is an example of water and ice. This is an example of a chemical that is not water, and generally for most substance, the density of its solid, because it's much more compact, is going to be higher than its liquid form. Here is a graph of the density versus temperature. Water, the density is low for the solid. Once you get it to a liquid state, its density becomes higher. For carbon tetrachloride, in the solid state, the density is much higher than its liquid state. The surface tension for water, because of hydrogen bond, is also very high. What happens is that at the surface right here, the water molecules are attracted to each other, so it creates a tension. That's why when you have water against a wax surface, it beats up, because that's how it maximizes surface tension, right here, due to hydrogen bonding. The capillary action, that's because capillary action is the degree by which the liquid goes up a tube. What happens is that the water molecule is attracted to each other. In order to keep this attraction as efficient as possible, it has a concave up. And then if you're taking water and you have it attract to carbohydrate, it can hydrogen bond to that too. So there's competing forces here. The water is going to be attracted to carbohydrates. That's the cellulose of like the stems of trees. And so there's going to be an attraction there, but in order to maintain that cohesive force, it's going to try and keep that surface as maximum as possible. And what happens is that it tends to rise up in order to do that. For water, the adhesive force is going to be greater than the cohesive force. For mercury, the cohesive force is greater than the adhesive force. Water has a high heat capacity. Why do you think that the temperature of planet Earth is much more mild compared to the temperature of the moon, and it's about the same distance as the sun? And that's because water can absorb a lot of energy, and therefore the temperature doesn't change that great. Even when you compare it to the surface of Mars, Mars is further out from the sun, and yet the temperature fluctuation in Mars goes from 220 to minus 81 degrees Fahrenheit. Planet Earth, basically the temperature is pretty mild. It has an average temperature of 59 degrees. Imagine a planet without water. The temperature, if we were solid rock, then there would be no substance to absorb the heat from the sun. The average temperature, daytime temperature, would be 300 to 500 degrees Celsius. At nighttime, the temperature would drop drastically, because that energy that the surface received would just bounce off to outer space. So the water on planet Earth is really important. In fact, water keeps us cool. When water evaporates, it pulls, for every gram of water that evaporates from our skin, it pulls 540 calories. That's why when we perspire, we feel cool, because that amount of energy is being removed from the surface of our skin. The vapor pressure, well, for water, it's one of the lowest. Why? Because water does not tend to evaporate very efficiently. And so the vapor pressure of water tends to be low compared to, say, a chemical like ethanol or some sort of organic chemical. Because the organic chemical has weak intermolecular force, it easily escapes to the gas phase. Water, because of its strong intermolecular force, doesn't easily escape into the gas phase, and so its vapor pressure tends to be low compared to, say, gasoline, which has weak intermolecular force. So again, this is a depiction of the heating cooling curve, and I hope that you have a better appreciation of what this particular curve is trying to illustrate. And this is a summary of what we talked about in this chapter. We talked about intermolecular forces, and the thing to remember is that intermolecular force is the force between chemicals, from one chemical to the other. It's not the force within, it's the force between. And the major type of intermolecular force we studied are London dispersion force, which is ion-induced dipole, and all chemicals have London dispersion force as long as it has electrons. We've talked about dipole-dipole, DD, and this is between one polar chemical and another polar chemical. Only polar chemicals will have dipole-dipole. Hydrogen bonding. Well, if it's got hydrogen bonding, it's also polar, so it has dipole-dipole. It also has electrons, so it has London dispersion force. But what makes hydrogen bonding unique is that hydrogen is bonded to an electron, directly bonded to an electronegative element. And so when you see this, you can check off that that chemical also have hydrogen bonding intermolecular force.